Yep, I think it's recording.
You got the red lights.
All right. So thanks everyone for coming out tonight. Got a good talk. Couple of quick things. We kind of have a blog that we set up. So we're going to try to create a little bit of a community around that blog and be reaching out to everyone through the Google groups for anybody who wants to contribute against the post or wants to cross promote. Trying to create kind of hub for this sort of material in Virginia. So that's new, so keep an eye out for that. If you haven't signed up for Google Group, definitely do so. Just go to datahackers.org, just find all the links and everything you need. So tonight I've got John Berryman, who you know, he's been out with us before.
I shaved my head, so you might not know.
You might not recognize.
It's actually evil John Berryman?
Yeah, it's an evil doppelganger has come out now, so don't confuse the two. And his colleague Doug Turnbull, who's they work together at Open Source Connections in Charlottesville. So I'll let them tell you a little about themselves and then kick into their conversations.
All right, cool. So I guess first things first, let's just go into some introductions. So hi, my name is John Berryman. Open Source Connections is the company that we work for. The name at this point is a bit of a misnomer. We don't connect people necessarily to open source, unless it has to do with search and big data. Largely what we do now is help commercial side or government side with search and big data. One of our largest clients right now is the United States Patent and Trademark Office, and we're building the future of patent search for them end to end. So on the data side, we're cleaning up the data, getting it into index. We've got a little API layer that is keeping everything straight, and then we've been working with a really bright lady from Berkeley on user interface, and our JavaScript team is working on that. So end-to-end search. And what you're getting ready to see today is how we're taking strides a little bit more into the big data side of thing and analytics itself, which is obviously the core to your group. My part of this spiel is going to be more of the academic approach, and
I will be John's plumber.
data plumber.
Data plumber, yes.
Doug Turnbull. All right, so.
That's me.
All right, so the big idea tonight, I will tell you how we used Mahout and Solr and a little bit of pain to give Solr the ability to do semantic search and recommendation. So during this talk, we'll talk about the problem statement. We'll motivate the foundation a little more with some of the more mathematical aspects, which I think you guys will probably be very interested in. We'll go over the ideal approach and how easy this is to do. And then we'll go through the cruel reality, which is like the actual practical problems that we ran into. This is labeled demonstration. It's a little bit of a misnomer because we're still kind of in the process of figuring this out. But we'll give you some idea about where we are, and then we'll tell you where we would like to be headed. All right, so the problem statement. First things first, and some of you guys who were here last time probably got a little bit of this for me, but it's good to understand a basic model for what search is. So how does search work? Let's look at a really, really simple document set. Let's say I've got 3 documents. Brown foxes jump. The quick fox runs. Brown dogs are running. Okay, so there's my 3 documents, and I want to index them and be able to search for particular documents that contain particular terms. So the first thing that the search engine does is it takes those sentences and it chops them up and it enumerates what terms are inside each of these documents. So instead of having a sentence, now you've got kind of a matrix where document 1 has brown once, fox once, jump once. Document 2 has blah, 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 quick 2 times. So it's right here, it's very simple. In reality, it'd be more like the strength of how important that term is in a document. We're not finished yet. In order to make this quickly searchable by a search engine, we need to basically transpose this matrix, which gives us the inverted index. You'll see that the values there are the exact same as here. We just flipped it about the diagonal there. And this gives us the ability to quickly look at which documents contain particular terms. So, for instance, this makes search quite easy at this point, at least basic Boolean search. If I wanted to search for any document that contains brown and fox, then what I would do is I go to this really quick data structure, find find Brown, pull out the vector there, find Fox, pull out the vector there, and basically they're bit vectors in this case. So when I say I want Brown and Fox, then all I have to do is AND those bit vectors together, and that gives me the resulting bit set is whatever documents actually exist in both. And in this case, it's just the first one, and I return document 1. So that is a real simplistic model of how search works. But there is an issue. What's missing? So when you get down to it, what I just showed you, the search engine itself does not really know what any of these terms mean. It's just a glorified token matching system. Very efficient, but all it can really do is just match up the tokens in your query with the tokens that it finds in the documents. You can't match on meaning. You can't ask it, I want something revolving around computer science and have it give you any meaningful result back. It'll only look up computer science. So, as an example, consider these documents. Yellow banana peels. A banana is a long yellow fruit. This mystery fruit is a long and yellow and has a peel. What happens if you search for banana? You don't get back document 3 because even though the context really is hidden there, latent there, the search engine does not have the smarts to provide document 3 as a possible outcome. So some of you guys, maybe you came here more interested in the recommendation side instead of the semantic search side. Semantic search is searching for words and finding documents with matching meaning. Turns out that recommendations is actually a very, very closely related, in some cases, identical problem. Recommendations is going to be common if you want to have your community, you want to make recommendations to your users, your clients, your customers about the next product they should buy. And you can't just recommend garbage, you got to recommend something that is statistically likely for them to buy. It turns out that if you have a matrix of terms versus documents, you can treat it very, very, very similarly to a matrix of videos versus user preferences. It ends up being the same math to figure out which document contains words of this meaning versus which user should probably watch one of these movies. So in the course of this, we'll be talking about one or the other, but really it applies to both.
Wait, John, sorry to interrupt you.
Interrupt, please do.
You say you want an interruption?
I want interruptions.
Earlier you said you could just do the AND operation. So in the left, is there counts of occurrences within the document? Is that something analogous on the right?
With the AND operations, that was actually just presence or not presence.
Okay, so just if it's non-zero, it's true. And then
The higher order model of a search engine takes into account how many times a term occurs in a document. Yeah, and that corresponds kind of to user ratings. That's what this would be. And the zeros in our case imply the user has not actually seen the video yet. Practically, you probably want to do something slightly different for that. But in either case, both of these documents are sparse. Most documents don't have every word in the English language, and most users haven't seen every movie. And the goal is to find out kind of what's in between. What people would like to see if it was there, and what documents should contain these words if only they contain all the words with a related meaning. So roughly speaking, these are very, very similar problems. So we're starting to get an idea of our goal here. If there's some way that we can pull this term stuff out of Solr and we can blur the meaning, then maybe we could shove all this back into Solr and make it searchable. We still don't know quite what we're talking about yet. It's very vague. So we were starting to get an idea of what we want to do. In order to make it a little bit more understandable, I think it's good to step back and look at some of the math involved here, and hopefully I can convey it in a way that you understand kind of the meaning here and what we're getting at. And then our goal will be a bit clearer. So what does it mean to blur meaning? Probably the best way to explore this is to look at an example. And here on the left, we're going back to the recommender side because it's easier to understand intuitively. We have, I'm sure you can't quite read that, but the numbers don't quite matter. We have a small matrix that represents a set of movies and a set of users who watch the movies If you want to understand what's going on in that matrix, one of the best tools that we have is called the singular value decomposition. And basically what it does, it's a linear algebra operation that takes this matrix and turns it into these three matrices. Now, you might be asking yourself, why on earth would I trade in these nice pretty numbers over here for lots and lots more numbers that I don't know anything about what they mean? The reason is because you can actually apply meaning to these numbers, and it can become more intuitive for the way you usually think about it. So instead of thinking about how a user judged the movie, how movies are related to users, we can actually put kind of a middle space in there. We can say, how much does a particular movie belong in a particular genre? Drama, horror, romance, whatever. How strong is this genre in our data set? If most of our movies are action, then maybe we get a high number up here, which corresponds to action. Maybe if the next one is kind of romance, we get a number here associated with romance. These diagonal values, a kind of intuitive way of presenting it, they represent how strong each of these components of the movie set actually are. And finally, we do need to convert it back to users again. So for a particular user, how much do they enjoy a particular genre? Once you multiply all these three matrices back together, you actually get the original matrix again. So if you're like me, you might still be saying, well, okay, I kind of get it, but the whole singular value decomposition thing, matrices are a little bit obtuse, are a little bit opaque. It's hard to figure out quite what's going on. One way that I try to combat that for myself is I actually zero down to like one number, and I try to figure out what's going on for that number. And hopefully we can make this clear with an example about my relationship to Chucky, Child's Play. All right, so in this matrix we have users and videos. And everything in this column that's now off screen represents my votes for particular movies. And everything that's in this row represents everybody's votes for Chucky. So when we apply the singular value decomposition, so the individual number, back up, the individual number itself, 2, represents my personal feelings for this particular movie, Chucky. That's what that one unit represents. Value of Chucky for John. So when you apply that matrix decomposition, if you really just kind of take it down to an equation for one number at a time, you've got a summation over every genre of how strong Chucky is in a particular genre times the strength of that genre in our data set times how much John likes that genre. And so let's look at an example of what that means. If your biggest genre in your data set is action with a value of 5.3, then Chucky's value inside that genre is 0.1. He's got some action associated with him. My like of action movies is fairly high, 0.1. Multiply those all three together, just like it says here, and you get 0.5. Okay, so we're building up my score, we're building up close to 2. Romance is the next category that's the strongest in our data set. The overall strength is 3.5. The value of Chucky in the romance data set is 0, because he's not a very romantic, it's not a very romantic movie. Chucky's Bride, however, quality flick, you should see it. And also the value that I apply to the romance genres, I like it half as much as action. We keep going. Horror is not nearly as popular as the other things, but Chucky really lies dominant in this category. He's very closely aligned with that, and I like cheesy horror flicks, so I actually rank fairly high right there. Multiply it all together, you get that contribution of the horror genre. And you keep going with less and less and less popular genres, until finally you get to kind of noise is really what it is, but you get to very, very, very specific genres, such as scary doll movies as a genre. There are a couple. And in this case, Chucky really, really is dominant in this category of movies. No one really cares, though. The genre is very weak, and not so much for scary doll movies. So even though Chucky is so strong in this, it really doesn't matter. And it begs the question, why do we so low of importance in our data set. And that one idea, being able to chop away the noisy data, the less useful data at the end of our data set, is how we're going to make recommendations to people, and it's how we're going to find documents that follow your meaning as opposed to just the terms that you search for. So if we look back up at the matrix again, what does it mean to chop off the low meaning data? Basically, it means to get rid of this, to turn that value in the genre matrix to 0. When you do that, and you're multiplying out these matrices, effectively what you do is you cut off large chunks of both of these matrices. And in real matrices, these are all the movies in your data set, all your users, and the part that you're chopping off is giant swaths of these matrices. So instead of multiplying together 3 matrices that are, million by million type order, this becomes like 1 million by 200. This is 200 by 200. This is 200 by 1 million, something like that. It becomes much more tractable. And after you chopped off this data and push back together, multiply together the leftover matrices, you get a matrix that isn't the same as the original matrix, but it is the closest approximation that you can have for chopping off the minimal amount of data. And what it tells you, the differences between these two matrices are often informative, because in this is a little bit small, I'm sorry, but in the original matrix where the user did not watch movie 0, by doing this rank reduction, by doing this kind of blurring of meaning, we find out that the user probably should be watching that movie, because it's if you look at it with a broader brush, with more blurry glasses, and you look at all the users who have watched a movie similar to this user, they all watch this and like it. So we give it a score. We think you will vote this. We think you will rate this movie this much. Turns out that all this madness is not called blurring. It's called rank reduction, and that's going to be kind of the cornerstone for how we approach our work. So just as another take, I like as many ways of looking at a new idea as possible. I really like to be able to find geometric visual analogs to whatever I'm looking at with these matrices, because matrices are not always the easiest thing to understand. One way to do that with these matrices is you can think of every row inside the movie user matrix as being a point in high dimensional space. Now I've only got 2 users in this matrix, so you can actually visualize it, but each one of those rows can correspond to something like that. Whenever you apply singular value decomposition, basically what that's pretending is that these dots, these documents, these user ratings, fall in kind of an ellipsoid distribution in this space. And so whenever you do the rank reduction, basically what happens is you take all these points inside of some space, you shove it down into a plane, and pretend that all the dots are actually in that plane right there. I don't know if that's easier to understand or not, but I always like kind of having a visual thing to anchor back to. So singular value decomposition is the thing I just brought up, but that's not the only player in town. We've got, it's good because it provides a fairly easy way to understand the way we're breaking up these matrices. But there are other things that are of interest. Alternating least squares is really appealing to us because it was the technique that was used. It was one of the dominant things in winning the Netflix award recently, the Netflix challenge, which was basically for making a recommender engine. There's also kind of a randomized way of getting at things called the stochastic SVD, and there's plenty of other rank reduction algorithms that could be applied, all with different qualities. So we've started to get a little bit better yet understanding of what our goal is. The previous time I showed you this slide, it was pretty blurry, kind of what we were trying to do. Now it's become a little bit more clear exactly what we're going at. rather than just pulling terms out, we now know that there's this idea of a term document matrix. And as Doug is getting ready to show you in a second, we understand how to pull that out of Solr and into Mahout so we can play with it. Once we get the term document matrix out of Solr, we need to be able to rank reduce the matrix and then shove the leftovers from this rank reduction back into Solr, where effectively, in my earlier parlance, you can search over terms and it's kind of blurry. You actually get to see documents matching by meaning as opposed to just token matches. So that's it for the theory, and now Doug's going to talk a little bit about the practicality. And
now it's time for practice.
Yep.
Which is way more complicated. Okay, so when John and I started thinking about how this would be a really cool thing to do, the first thing we did was we had heard that Mahout kind of has this capability. So we hit Google and we thought, okay, well, we're going to start with something that has a Lucene index, Apache Solr, which is the search engine we're familiar with. We need something that can extract from that. Google tells us, or the Mahout documentation tells us, there's this great thing called Lucene vector that can point it at a Lucene index that is behind Solr and will pull out sequence files that Hadoop understands. And we'll get our term vectors out that we need to do rank reduction. Next step, of course, is rank reduction. We're really excited to find that Mahout supported singular value composition. So we could split out the matrices that John was talking about. And we were excited that Mahout should be able to multiply these matrices back together after they're rank reduced. And finally, we were just going to do something simple where we were just going to throw a bag of terms based on the blurred meaning. So if banana got in there, banana was going to go in the yellow peely fruit document to have an extra search field for people to search on. So we felt pretty confident in our approach. Of course, those are often famous last words. Here's the cruel reality. This is what actually happened. Okay, so this is the Frankenstein's monster that we created. It ended up working for the most part. So, based on that, yeah, by the way, we're nudes, so we're learning too. Turned out we had to index into two different paths. The reason for that is when we throw the blur matrix, the banana, at the yellow peely fruit document, we want to use a feature called Solr atomic update, which basically is you can update it without reading the entire document, modifying one field, and updating it again. That's super convenient, and it's just a lot less cumbersome. So we needed that for Solr 4.0. Mahout's Lucene vector is based on what version of Lucene Mahout is built against. And that only supports Lucene Solr 3.6. So we kind of had to go through paths with two different search engines, two different versions. Which isn't a huge deal. We basically copy-pasted the Solr configuration in two different places. The next step was to pull the vectors out. This is the actual command that you tell Mahout to turn your Lucene search index that Solr has created into term vectors. What it's creating is what's called a sequence file, which is just a binary method that a lot of you guys, I'm sure, have worked with, of key value pairs. Keys, we were hoping that the keys were something like an ID from the search engine, and the values would be just a sparse vector. The values were fine. It turns out, though, the keys are just linear rows, 0, 1, 2, 3, 4, 5. And we had to use this, we had to create our own dictionary that converted this row index into the vector, the document ID that corresponded to that vector that was like embedded within the vector. And we also had to store away this other dictionary, which each column is a term. So column 0 is Doug, column 1 is John, column 3 is yellow, column 4 is banana. We had to store away this other dictionary, so we had to keep these two extra dictionaries around just to refer back to it after we blurred and then multiplied back our matrix. The next step was rank reduction. So we looked at 3 different solutions. We started with SVD, which we were really excited. I mean, it's SVD, that's what our whole talk is about. Found that, turned out that that only reduces one of the matrices. So it returns the one left values, and what that's actually really built for is more clustering. So it's more about defining genres than necessarily giving you 3 matrices to play around with in a more generic fashion. Parallel ALS looked really cool, but it was not, the input format that it required was the same input format that Mahout's recommenders require. We have a bunch of sequence files and term vectors. It expects the CSV user item rating. So we decided not to go with that. And finally, what seemed to work that was seemed to be purposely built for this application was the stochastic SVD, which is what Mahout calls SSVD. And this is just the command that you have to run, basically taking the output of our extraction from Lucene and outputting it to whatever. It's funny, sometimes they call it tempter. What Mahout calls tempter is actually outputter. Okay, so great. We've got a directory. We've got a bunch of sequence files with a couple of different matrices that are rank reduced, because that's what the last step did. And we just need to multiply them back together. And actually, surprising to John and I, this is where we wasted, or I guess spent, most of our time.
Wasted's fair.
Wasted. So when you get just how SSVD works, you've got to transpose the right matrix. And so we're trying to do that. So we ran into, there's a lot of slides here about, angry drunken coding and thrashing violently and punching holes in walls, et cetera, et cetera. The long and the short of it is we ran into a lot of problems in Mahout because some jobs, like the Lucene vector dumper, give you keys of long writable to vector writable, which is the vector wrapper in Hadoop. Other jobs, like the transpose job, want you to accept an int writable. And it's not like there's implicit conversions between the two. They're both classes and they're both extremely type safe, which is really annoying. So John coded up this custom long to int key converter, which just is as dumb as it sounds. It's
well
really
done,
it's amazing. It's like reading Shakespeare. More thrashing, blah blah blah. Yeah. At one point we were like, all right, let me take this MapReduce cluster and see if we can understand how 2x3 matrix can be multiplied, because we were just so frustrated with how it worked.
And the irony of using a Hadoop cluster to multiply matrices that are 6 elements each.
Yeah, and we have to wait for it to do its map job. There it is. So we finally kind of figured out something that worked, and this is the command that it turns out you have to run. And it's kind of interesting how there's a side topic here, how matrix multiplication works in Hadoop ecosystem, that if anyone's interested, you can come and ask me about. I was talking to Peter about it earlier. We eventually got, so after days of head banging, probably like a week of banging our head, we finally got our matrix, blurred matrix, multiplied back together. So we started looking at that, and the next step was to pull that into Solr. So that was a pretty simple couple MapReduce jobs that we wrote. That wasn't too hard. Take the 2 dictionaries that we wrote out earlier, look up the column for the term and the row for the document, and put together a bag of terms for anything that has a blurred value. You can set a threshold. We're just setting a blurred value greater than 0. So anything that's present. We're doing pretty stupid stuff. And so we've got some interesting results so far. We're still kind of in progress on playing with these ideas. One of the fun things that we got, how do I get out of sorry.
It's a Mac.
How do you use a Mac? Is there a user group for that later?
Oh my goodness.
There's a support group for those of us who
See, he can't
don't do it.
It's a 12-step program.
Oh, really?
Yeah.
And then if
Except you're not in control of anything.
Yeah.
Wow. So apparently we're like running through, check out this little chart on the right, left there.
Whoa, we're doing the performance mode of Prezi.
Yeah.
How
So,
did you do that?
I don't know, we broke it. All right, anyway, there's what you want.
So we're just learning about computers?
It's pretty cool. Just before we get home.
Okay, so we were doing rank 5, which means we decided that 5 genres were okay. And I should step back and say the data set that we were playing with is one of the Stack Exchange data dumps. They put a data dump out for people to play with. It's basically all their questions and answers and comments. And we liked, because we're all nerds, we like the sci-fi Stack Exchange site. And just with 50 posts, just playing around on a small data set, it's pretty cool because with these genres, which are in SVD land, that's also called a concept, you'll start to see some trends here, like concept 0 is fairly grouped around Star Trek. So if you go through here, you'll see things like Picard, I think I just saw.
I think the stronger ones are at the bottom.
Yeah.
Yeah, see the score.
Count Nemesis, Data, Trek, Enterprise, Trek Movie, Star, Roberto, I think he's an actor, Picard, Insurrection, Ambassador. These are all, it's really cool because these are all Star Trek terms. Concept 1 appears to be, and keep in mind, as John showed on his, that these are sorted based on strength. So in the first 50 posts of the sci-fi Stack Exchange data set, Star Trek is a little stronger than Star Wars.
Wait, so Doug, can you step back a second? What are we?
Sure.
The term concept here is introduced. The context is that these are terms that would likely appear together.
Yeah. So this is. What's that?
Maybe show the term genre.
Yeah. So this is the same as the genre movie matrix.
Do you remember how we took that one matrix for terms and documents, and we spread it up into terms and components, component strength, components for documents?
Yeah.
Okay, so basically what this is one row out of the now term component matrix, or term.
What's interesting about this is that with the genre stuff, you would typically expect that that would be in your data set, that you would have inputted there. But
So
here you're extracting it and
exactly.
learning this by analyzing the matrix. And so concept 1 is just a placeholder. It could be whatever. There's maybe a term here that we could replace that with that would somehow say, oh, Star Wars is the concept.
So that's when he was saying genre. Really, it's a statistical genre. You might, for some reason, your data set might decide that horror movies with Sylvester Stallone that are also slightly romantic. I mean, you might extract that thought because somehow in your data set you just love Stallone romance movies, and that's what's in your library of stuff.
Yeah.
So we know it's a romance movie in those cases. And I was wondering, so when you have that example of like a Netflix problem, you often have the categories, ontology that's already given for each of those elements. And in this case, we're saying there's no preconceived ontology. There's simply things that happen to statistically correlate.
Yeah, so when we're talking about like genres, it's easiest for me to convey the idea in terms of genres that we're comfortable with: action, adventure, comedy, blah, blah, blah. The truth is, the computer we think of genres as everything that correlates together. Action, you have people punching each other, and you have stuff that seems to go, when it's called action, you have these features. When a computer sees a document, then it does the best it can, but it's a kind of a simplified version of what we feel like a genre is. So for the computer, in this simple case with actually a very small data set, unfortunately, it did a pretty good job about pulling out this vector and saying these terms covary a lot, and they all happen to sound like Star Trek. And then the next set, the ones that covaried a lot sounded a lot like Star Trek. Wasn't perfect. There's some things that, like Asimov is in there. But
yeah, it's interesting because the Foundation books, because they refer to a galactic empire, they somehow get brought into this too. So it's at this stage, it's more of a clustering thing, but more than like it's not content aware. It's completely content agnostic.
I haven't used this particular method for class and group with your Star Wars genre or Star Wars concept is they distinguish between the other concepts. So these don't, there's not overlap between
Right.
them. So it's looking for the things that
Well, there
they
is,
go
but
together, but then they also distinguish
these
between
vectors
them.
are orthogonal from the
Yeah.
other vectors.
So the goal here is actually to create a set of orthogonal vectors. You're like, we're kind of forcing some things to be a little more orthogonal by rank reducing at the end of the day. So that these documents will have in the stuff that's merged back together, these guys will be emphasized more, and some other stuff might be emphasized less.
Do you know how much you cut out of the matrix by the process? Do you have any sense of
It's
what
probably
was
better
suggested?
to talk about how much you should cut out as opposed to our OMB search case.
Do you figure that out based on how much overlap there is?
It's so last time we presented this, someone said, well, how do you know exactly which rank to chop it off at? Because really, when you look at the matrix, it doesn't like big numbers and then suddenly little numbers. It just kind of slowly goes down. And so the best I've seen is just kind of like, here's a rule of thumb, and I don't necessarily like that, but they say that rank 200 for text documents is reasonable about capturing what you want. If you cut it off before that, the performance drops off quickly. If you cut off after that, the performance drops off slowly. But English is kind of, natural language is dirty. There's synonyms, there's polysemy, and all sorts of other mess. So it's hard to really theoretically know, right?
Yeah, it's one of those things where if I was to build this in a search application, this happens to us all the time. There's so many knobs to turn that it's like you would have to make something that would have to be in front of the customer.
You can almost A/B test it and see
Exactly.
how much people took your recommendations, or how much, like when you were showing that first slide where it was like, okay, this person had a 3.8, it should really watch that movie, but without rank reducing, it was like, you didn't show that.
What's
Yeah.
the cost of setting this up if you wanted to do A/B testing like that?
Well, you said A/B testing, and like cringe just a little bit. These are big map reduce jobs, or once you actually did it at scale. This is one, but you're doing a singular value decomposition, which you do one row at a time, but you're doing it on matrices that are potentially like million by million type thing.
Well,
So
one of the other things, I think, correct me if I'm wrong here, but I did something similar to this in the past, and what you end up with, like 5, is what you guys chose, I think. So that's like the number of dimensions, right? So like you're comparing points in a 5-dimensional space, and so like the multiplication necessary to determine how close things are grows as you increase that. So if you use 200, that's a lot more than 5.
In which case, it's not really an opportunity for tuning if you can't really compare.
well,
If it costs that much to set
If
up
you had
your...
a static data set,
A/B testing would be rough. And one knob you have is like where you chop off the rank, although it's just not really clear. So you'd have to like run it a few times.
it would be hard to have A, B, C, D, E, F, G, H, I, J, K testing.
Yeah.
A/B, if you said, I'm going to do one with 100 and one with 300. I mean, you run this job once, hopefully, probably not, you probably have to debug it, but you do it once, and then it's just part of your search application. You have the sequence file that you could shove your bag of terms into your search application just to give it something to sure to match on. Then it's not, you don't have to run a Hadoop job all the time to get it back to where you are.
Obviously, I can explain. So, what are you using for the calculation algorithms for the semantic stuff?
The algorithm that we were
Co-working 804.
Co-working
One word.
So you guys, was there any sort of like plan to fold in new stuff? So like maybe I'm lost here.
Open source or?
Well, so maybe you get a new document, right? And like, so how do you have to just rerun the whole thing, or do you have some
that's
way?
a really good question.
That's a little bit challenging. I read a paper that was talking about if you do singular value decomposition, there are ways. There's kind of like the cheapo version that's like a fairly simple matrix multiplication or two to append rows to the end of these things. But you slowly run away from the nice qualities that you
Yeah, you
had.
must have read the same paper I did, right? Like the more you fold in, the worse
Eventually, you're going to
it
bring
gets.
down the job, basically.
Yeah.
The paper I read seemed to indicate there's some slightly more computationally intense method that you can get closer and maybe even achieve what it really would be without running the whole SVD over again. But I haven't dug deep enough.
And one of the other things,
It's a statistical problem. It actually goes back to the earliest. If you ever learned how to like compute a standard deviation, there's a theoretical formula and the computational by hand formula. The actual reason the theoretical formula lasted was ultimately you had to go back to the theoretical formula if your data set gets too large. Otherwise, your round-off error essentially blows up. I know that sounds abstract, but it's exactly the same problem. You're trying to leverage the difference. It's such a large number. You're talking about adding a nuance to a massive number and trying to balance that out. And so unless you unstructure that number in some way so that you can do that so that information isn't lost, because now when you're talking about adding 100,000 of this nuance number to a large number, that's actually making a difference, and that's why the decomposition, why it fails ultimately.
Right. So is there any way to get halfway there? Like,
well, I suspect that the same learning curve will apply here. Is that someone will actually kind of evolve to a way of decomposing this in a less computationally sensitive manner. I mean, if you think about what everything that you're doing here is about, it's about aggressively pursuing massive computation. And ultimately, that always runs out in the statistical world with the step back saying, well, that was great, but it turns out we did lose something and we have to come back a little bit for it.
There's actually another method that we don't cover in this presentation called random indexing. That is maybe more practical, and it's nice because you can update things a little more easily. I haven't gotten, I read about it a while back, and I wanted to get a lot more into it, but I haven't.
Yeah, and the reason that works, just to kind of give a quick version as to why that's effective, is because you have time correlation when you keep adding something on. So you're in essence leveraging the latest state of things, and you're ignoring everything else that happens. So if you step back from that and you randomly apply it over time, you don't have that sort of point in time waiting that's messing everything up.
Right.
Does that make sense?
Yeah.
So, I mean, the point is, it's kind of like taking a random sample all of the time, every time, because that's going to get you a better idea of now you can weight your deviation and say, well, if we had a sampling of this deviation, and we're going to be able to call it that because there's no what do I want to say? There's no rhyme or reason to the latest things that you're looking at, then you're free to actually make an estimate and push that back up to, recalibrate your values.
How much of a random sampling would you need before you're dealing with too large of a sample and then either or too small of a sample? That makes sense. Because I mean, when you give up like an entire data set, are you?
Well, the challenge is you're making estimates upon estimates if you keep doing that. So you have a different problem. You have in essence the opportunity for a complete bifurcation to happen accidentally. May be unlikely, but it could happen. So you would instead want to go with you know, you would want to have a periodic recalculation. But you could probably go further with that than you could, you know, dealing with serially correlated adjustments.
What about, I saw in the terms there that, you know, I know Solr does stimming and stuff for you,
Yeah.
but then I understand, or I gather from what I know about this, that, you know, the LSI doesn't really need that because it's already going to sort of map terms that co-occur without them being identical. So did you run it with stimming and without and see what the effect was?
We did not try to compare the two, and honestly, what you're seeing here is still, we need to get a little further along before we have
Sure,
to
no, I was just curious.
anything. But stimming and the LSI are going to serve a little bit different function. Right now we have, I think with this data set, we have 36,000 terms. It's a fairly small data set. And it was very, very, very highly stemmed and stop words, so we cut out all the cruft. If we hadn't stemmed it, then it would have had, you know, walk and walking and walked, and all the variants would still be in there. The data set would have been a lot larger that you'd have to crunch on and get the singular value decomposition out. And really, when you already know that all those things should be compacted into one unit of meaning, you might as well do it and save your computations. And
Well, I mean, I don't know, that can be a subtle point, maybe, you know, because, so maybe like Walker, the term does not recur or co-occur with walking. Like maybe those terms semantically are very separate and occur
gives people
in very different documents. And so, and even like wind and wine, I mean, I guess it would be interesting to.
Yeah, and so that's very true too.
This opens up an opportunity, and I apologize for the sick thought in terms of the next type of hacker, but when I see like these lists and the correlations and the grouping, it makes me think of like religious apologists, and their argument method is to essentially warp and cross over terms. You know, so for instance, if a Mormon apologist is going up against a, you know, very world-renowned scientist, they will introduce someone like that as worldly. And the difference is that when they speak that word to a crowd, that's a crowd that has been programmed to think of worldly as a negative thing. Whereas essentially the supporting crowd of the, you know, of everyone else, sort of the scientific side, would think that that's a very positive thing. And in essence, something like that would crosswire this. I mean, it makes me think of the concept, and when I see, for instance, this crosswire, I'm loving seeing 1952, 1953, and, you know, in that mix, that's world's meeting for very interesting ideas, but an apologist, in essence, could get in there and completely crosswire. It makes me wonder if you could crosswire
Like if you
Netflix.
could create a dictionary so that people would say, well, if I can use this word, it has good meanings with both crowds. That'd be great for politicians,
Yeah,
right?
Well, no, but that's exactly what they do. That's exactly what they do. No, people already have
It
those
has the
cross
appropriate
meanings
meaning
in
for which
their.
whoever hears it.
Right,
So you
right.
want to
So-
And the analog
So
here would be
if
like
you-
search engine optimization, right? So like you'd be stuffing your document with terms that are going to show up when people search for this other thing.
Yeah, the two sides of it is, if
they
you're
already
doing
did
this
that.
kind of analysis, you're going to learn the key terms that, in essence, could undermine Netflix.
So you could find a term that you're not aware of the meaning it has by looking at its neighbors that would give that you are aware of those meanings.
Right, yeah. So I mean, it's sort of when worlds collide and things have completely different meanings. The words that aren't out of place here are the crossover words, as you said, like what was it, the Empire, Galactic Empire, or whatever. I'm a little out of date.
If you
with-
say empire, then two sets of nerds, it's going to be two different
Right,
things.
right. Yeah, so that's, anyhow, it's just, it's fascinating to me, the idea of being able to trip up the next level of intelligence in this way.
Is the code for this, is this all in one repo on GitHub somewhere we can see?
Not at all. We wouldn't show anyone this code.
Proprietary. To be hired for things.
So actually, there's a little bit more. We've kind of gotten away from the.
So
just saying, hey, this
That's
is,
excellent.
Solr is
It's done.
great, and we can
It's done.
say for the body field, the original non-blurred text, we can boost that versus the body blurred field. We can give them different weightings in search results. So if we match banana in the blurred field, but it doesn't really make sense, then hey, we can weight these things differently.
Wait,
We can also-
blurred is a term.
Blurred just means the rank
Rank
reduced
reduced.
matrix that's been put back together.
Oh, those are the two main.
Yeah, whenever you give this, the term document matrix to this big black box, which is not in GitHub, then it gives you back basically a new black box that has, basically gives you back a new field that you put next to the field that you based it out of, and it just got a lot more terms. It's based, another way of looking at all this is it's synonym generation. So it's
Yeah.
automated synonym generation.
Yeah, with a high enough rank, and so it's pretty much, that's what it is.
Oh, so it is one.
Now it's, ladies and gentlemen, John Berryman.
All right, so the previous couple slides are talking about how you use it with term document matrices, and everything that we talk about with semantic search is also, you can say, a similar argument for recommenders. But now since we can incorporate this stuff back into Solr, there's some kind of neat stuff that we can do with it. Solr is a search engine. So with recommendations, if rather than taking documents and terms, if you take movies and the user's rating of those terms, or users and the products that they bought or anything like that, then in order to give you a recommendation for the product that you're likely to buy, basically we have to do a query over that field of view. And that relates back to the products, and a recommendation as far as Solr is concerned is as simple as that. Where it starts to get really interesting to me is with Solr, you can also, you don't have to just be searching for the recommendation right now, but you can listen to what people are searching for, and based on their current search, and based on what they would usually like, you can take the search results from their current search and bubble up the ones within that search set that are more likely to draw their attention. So it's query-aware recommendations. You watch what they're actually querying over, scary dolls in this case, and you can boost the query based on what they would tend to like anyways.
Is it cumulative, or can it be cumulative? So I may make 5 queries, or 5 searches during a particular visit. Is it going to be able to take into account all of those search terms, or is it point in time based on one?
So there's ways that you could incorporate that as well. You can keep boosting what people have searched on in the past. Just make the most recent search the search, and then have boost queries. So we're talking about very Solr specific stuff now. You can keep adding boost queries. Say, whatever results would have returned from the previous search. Of course, you run a little bit of risk of muddying up the search if they decided to change topics. So I don't have to. You might want to include something to watch and make sure they're still thinking the same thing. All right. So next steps. A lot of our lesson here was lessons in pain, and I think Mahout was actually very difficult to deal with, but maybe a good portion of our pain was because we approached it with the batch scripts. Now I think to have a nice approachable library like Mahout wants to be, you need to make those things a little bit more friendly. They were not very friendly. I suspect that if we did get into the Java and kind of threw out some of the batch stuff, we would have a little bit better time. Our code would be a lot more organized, because right now since we're exploring, it was like, let's try this, and we've got like text files where we're just trying to lump stuff that we think worked, and it's a mess. So version 2.0 of this, we get rid of the batch scripts and embrace Java API. We've tried the stochastic singular value decomposition for algorithm here. You remember why we tried it? Because we were desperate, and it's the only one that worked.
It worked.
Yes. So I would like to look at other things. I'm particularly interested in ALS, alternating these squares method. That was the one that was worked so well with the Netflix challenge. In all the discussion that we've presented so far, we have treated the terms, the synonyms that we're pulling out, as if they all have But if you remember from that one thing that Doug showed you, we actually understand how strong each of these documents are within each of the genres or concepts. So Solr does provide the capability to incorporate that, and I think, rather than just being automatic synonym generation, having weighted synonym generation would make for a lot more semantically correct search. And finally, I want to sell the thing. I think someone can use it. It seems useful for the people that are digging through data to be able to, patent examiners. I wish we could sell the patent office on this. I want to find all patents related to this idea, not just these words, because they type in their own synonyms. They've got tons and tons of safe search that basically functions as synonyms for block. But also, recommenders are very popular. They've been publicized quite a bit with the Net Challenge, is probably the most prominent. But the ability to incorporate in this open source commodity software, Solr, the ability to make recommendations with the extra information about what they're searching for right now. I think that's a useful thing as well. So, zooming back out, we've talked about the problem, going over some of the math, which is where I really enjoy that part of it. Going over the practical implementation issues, the plans, and kind of the pain that we found when we came up against reality. We gave you a demonstration of where we are right now. Still got a long ways to go, and so we gave you kind of a look ahead into what we plan to do in the future. So that's where we turn it over to you guys. Is there any questions?
Destroy us.
Can you go back, just review, when you ended up with stochastic SVD, because it worked, how can you revisit how you knew that something was not working versus working? Was it purely just because you had some problems with how actually functioning, but from an analysis point of view, how were you making that determination?
So, basically, how it was lying to us. It has a singular value decomposition component. Look up the Mahout man page, and so we thought, cool, that's it. And the man page read just like we wanted it to. Except that it did tell us that it was only used for clustering, and it would only give us back the left matrix, the rank reduced matrix. Before we could do anything like we showed you, we really needed all three of those matrices. And just wasn't going to be there, and we'd have to make our own tweaky coding ourselves. The ALS, which is the Netscape-like thing, worked out. That's a really simple algorithm. I really like it. There is a demo. We ran it with a fairly large data set. Demo went perfectly. And then we started cracking into that. We would have to convert our data into another format that it was just not worth converting into. And
that's kind of part of the pain with Mahout is just the lack of cohesiveness between these different pieces. You have ALS that takes the item user rating, sort of CSV. You have SSVD, which takes, I think that takes, it takes whatever, I think, and vectors, and will output whatever the key was of the input into the left matrix, but it always will output int right to the right matrix. This kind of feels like a lot of different people's PhD dissertations, not individual, not like there's someone overarching saying no, everything must take this.
Series one code style.
Yeah.
In this doesn't feel like hard enough. What your actual outcome, the actual mathematical, that I don't think that this hits the level of having to get a canned software to do it. I mean, I honestly think that you could build a much more optimized one yourself. I really do.
More custom built, more purpose built.
Yeah, so and I suspect that it will, kick all of their asses in terms of speed and efficiency.
You have a lot of
And
faith.
what's that?
You have a lot of faith.
No, because it's just not that. It's not that much. I mean, it's just about having to set up the structure, and it also opens up. If anybody ever really large took this on, if you have that piece of it, I mean, that's the greatest ever GPU challenge I ever saw. That's
So how do you deal with the memory problems of matrix multiplication on a truly large data set?
You use a window, and you don't have to do. I mean, mean, basically, you have, the biggest challenge is that you have to do smallest forward, so it's just section, I mean, you just have to
Down
basically
product
do
or
section
sections.
window, yeah.
Okay.
So I mean, it's really
I would love
not,
to brainstorm about this later. This is kind of our first forays into stuff like this. And so if we can use GPUs and do what we did in like a nightly batch in 10 seconds.
yeah, no, I mean,
That's
it's
awesome.
exactly what a GPU is designed for. You just pull the window over, boom, move the window, pull the window, boom, but the flip side of this is to repeat history, in terms of what did we learn from statistics, because ultimately statistics came from an era where we didn't have the opportunity under any sense, ever attack a problem like that. Now we can attack the problem, but can I just point out that the outcome of statistics was that it's actually more accurate. In other words, if you subsample this, and if you do it intelligently, you're going to get a faster answer that makes more sense every single time. And I don't know what the size you're dealing with here, but I mean, if in essence you were to do a quasi-random reduction before you got into this, it's not only going to make it run faster, you're going to get a more sensible answer, because the same things that aren't cut out of that reduction, those are they're the things that should have been cut out in that reduction, and it's going to cut them out of that reduction. And so, it's a simple statement of saying, anybody who searched for this, the correlation, we're going to take the 100 terms of, most common correlation, and then we're going to run a reduction at that point, and we're going to, randomly sample within every one that hits that, that hits at least 5 of these terms, etc. That kind of thing. And I'm just throwing that out, but I mean, the point would be that you have an opportunity for a great reduction, but you're also going to remove a whole lot of noise, in that.
So plus side on both ways, right?
I think so. I mean, I think you're going to get more sensible outcomes. I mean, the point that I make here is just to say, we learned from the census. The problem with the census isn't that we get more data and that the data that we have is better. The problem is the data that we don't have kills us when you do the census. If you go out and you do a random sample or attempt to determine a population by catch and retrieve or something like that, you're going to get actually a much more accurate answer, and the bonus is that you know where your mistakes are. You actually know what you're missing in the outcome of it.
So in a case like this, is there, I mean, one of the things that seems like you want all of the non-reduced rankings because you're trying to provide a comprehensive result for search terms, right? And then within that, you could run your your recommendations as a boost query against that to try to give you a little more.
Yeah, you can tweak those knobs.
But to that end, and I agree, but let me spin this the other way though. So now a movie aficionado is coming at this, and they're not looking for the common answers, they're looking for the rare answers, okay?
Right.
And so if your boost query was, instead of a boost query, was a random, essentially an intelligently random reduction, rather than that one, you're going to get the same level of performance, but for that person, you're going to get more obscure hits, which is probably what they're looking
So
for
it kind
in
of
the first
addresses the
place.
problem I've heard a lot of my friends complain about is like, why does Amazon keep giving me the things that I already own?
Right.
Like,
Yeah.
You have some intuition about like what I might like, and just tease me with stuff that is sufficiently far out of this core set, right?
I also like, one of the things that I wish Amazon would do is, I'm so frequently recommended things along the same lines, not just that I own, but that I am extremely aware of, like the second entry in this series of books I'm reading. It's like, why is that a recommendation?
Right.
I want something novel and interesting and fun. And one of my frustrations with recommendations is it's it's just so predictable. Like, I ordered a Star Wars book once. Hey, look, I'm recommended 100 Star Wars books. It's like,
Yeah.
that's so obvious.
It's an interesting phenomenon. They took one technology and I think used it inversely. You take Netflix, the same thing works great. You know, I've seen a lot of movies. I have 2 kids. I can't go out at night, so I watch movies. So now my ability to say, Netflix, tell me what movies have I not seen that have a 4 point, or greater star rating on it.
Right.
And they're dead. I mean, their accuracy about knowing movies where I'll sit there and say, oh geez, well, I don't think I'm going to like that. And I can't understand for the life of me why you recommended that. But out of movies, and I love it.
The opposite problem, I got off Netflix because I could never, they stopped giving me anything with a greater than a 2-star ranking.
Well,
like, you just have bad taste.
You know what? No, I can tell you exactly what that is. Someone else getting in there with your movie recommendations. Because that's what happened to me. Was my wife got into the movie recommendation. I said, get your own damn account.
Well, in my family, it's my wife's account, and I'm the one getting it. No, you have to, you're married too. So if you were able to take a hybrid approach, and to say take a different, where you were going to do this kind of random sampling, can you integrate that output or something like that with Solr so that you could use the same presentation layer of this information, the same query layer against a kind of merged data set where you have the entire data set plus these recommendations?
Fundamentally, even though we propose to get Solr where it understands your search, it really still is just token matching. So if you can ever get it back into the form of, well, we're doing some magic with it and then we're giving Solr even more tokens, maybe with weights, then yeah, you can do anything that falls in that genre of approaches. One of the neat things about Solr is that everything in Solr is pretty modular. So if you're willing to crack in and start working with some Java code, you could probably get past this token matching thing somewhat. For instance, you create your own query handler that maybe it's got the right-hand side of this giant matrix in there, so that whenever someone types in terms, you can actually use this to convert to concept space, genre space, component space, and figure out what documents are closest in that space. And that's not quite term matching anymore. Not sure that's using Solr the way it likes to be used. But yeah, there's a lot of ways that you can mix and match approaches.
Just as let's say.
Wait. Let me go ahead. We'll end the official part of the meeting, and so anyone who wants to leave can leave.
Okay.
Cool.
Now
Quick statement then, before ending it. We're a pretty sociable group. You've seen us here a couple of times. We always like to meet new people. If you're ever in Charlottesville, please stop by our office. We serve as kind of a co-working spot. So feel free to stop by and tell us what you're up to. Teach us something, and we'll try to return the favor. And maybe we can work together.
What were you saying?
thank you very much for coming.
Oh, thanks.
I was just going to say that, like, one intelligent way of randomly sampling would be to take away, for instance, do a date sample.